In this video, we're going to talk about something in Lua called weak tables, which can potentially serve as a useful memory management tool in your scripts, especially if you need to cache values, but then clear memory once those values are no longer needed. Weak tables can also be useful for avoiding memory leaks in your games, which can be a problem you face if you forget to clear values being stored in tables, which is the most common way memory leaks can occur, when you cache values in a table, which are holding strong references, and you forget to clean up those values during runtime. Now let's first define what a strong and weak reference is in Lua. Now a strong reference in Lua is how values are referenced by default, and it's when a variable points to a value in memory. So when you create a variable like hello, and it's storing a table, right now this table has a strong reference being held to it by this variable. So that means for the entire duration of this script, this table will exist in memory. If I were to go and in the future update this hello variable to store something else, let's say it stores a new table, this is a new completely different table, this original table up here no longer has any references to it, so that means it's eligible for garbage collection. Now because all references in Lua are strong by default, in order to make a reference weak, we have to explicitly define it to be weak, and that can only be done through meta tables, or what we would call weak tables. In order to create a weak table, we need to set a meta table on a regular table. So here's our regular table, and let's go ahead and attach a new table. And inside of this table, there's going to be a meta method called __ mode. And this meta method is how we can control what type of weak table we want. And we have to set this equal to a string, and we have three different options. We can set this string to be k, which means all of the keys in the table have weak references. We can set it to v, which means all of the values in the table have weak references. Or we can set it to k and v, which means both the keys and the values hold weak references. And when a value is being referenced only by weak references, it becomes eligible for garbage collection in your game. So let's take a look at this in action. Let's store the result of this set meta table inside of a variable. We're going to call it our weak table. And this weak table is going to act as some kind of cache. Now, inside of a weak table, let's go ahead and create a key in here. And we'll call this my key, and my key is going to be another table. And we're going to use my key as the key, and we're going to set it equal to a value, like let's say a string of hello. And for this demonstration, let's first set the mode to be k, or weak keys. So that means that our table right here, even though it is inside of our weak table as a key, this key is only holding a weak reference to our table. So that means once this strong reference up here to our table is removed, the only reference to our table is going to be a weak reference because this is a weak table. And that means it can be garbage collected. So when we go to first print out our weak table, we're going to see our key and our value inside of it. But then once we set our my key variable equal to a new table, that means this original table up here no longer has any strong references, so it can be garbage collected. Now, garbage collection can take a long time to happen for weak tables, especially when there is no quote-unquote memory pressure. So to make some memory pressure, what I'm going to do real quick is I'm going to have a while loop that runs forever, and we're just going to have a table in here. I'm going to call it memory pressure, and we're just going to throw a bunch of stuff into memory by storing it in this array. So we could do something like table.insert inside of memory pressure, and we're just going to make new parts. And then to make sure we don't crash the game, we're going to yield here. And then to make sure I don't use up too much memory and crash my computer, I'm going to make sure to check if the number of elements inside of our array becomes greater than, let's say, 50,000 parts. That's a little bit too much, so we're just going to make sure we clear that table and start again. But this is going to basically put some pressure into the game because we're storing stuff in memory, which is going to force garbage collection at some point to get rid of any weak references inside of our weak table. So we're going to first print our weak table, and then we're going to have some memory pressure going on. And I'm going to have another loop down here that's just going to yield for 1 second, and we're just going to keep printing our weak table after we have remove that strong reference, and we're going to wait to see until our weak table becomes empty. So if we run our game and we look at the console, As you can see, our table is printing, but then now we're printing an empty table. So you can see the first 2 times we printed a table. Here is our table, and then here's our value of hello. And then again, we printed that table with our value of hello. But because we were putting some memory pressure, eventually at some point in the game, garbage collection happened. And because this table only had a weak reference to it because it was inside of our weak table, garbage collection was like, hey, I can get rid of this. And it deleted it. So that's pretty cool. Now let's actually take a look at something a little bit interesting. What if instead of storing the string here, I were to store another table, and inside of this table, I was to hold a reference to our first original key. So let's just say inside of here, we're storing my key inside of this array. Well, even after I update the my key variable to a new table, there is still a strong reference to our original table because it's being stored within this array. And because our weak table only has its keys with weak references, that means this is a strong reference to the original table and it won't be eligible for garbage collection. So if we run the game again and we take a look at the print or the output, look at that. It's not being garbage collected anymore. And that's because the garbage collector or the interpreter is realizing that there is a strong reference to this table here, and that strong reference is being held within this array right here. Here's our strong reference. Now we can change this if we were to swap the mode to K and V, so both weak keys and weak values. Now because there's weak keys and weak values, this is no longer considered a strong reference, so it's eligible for garbage collection. If we run the game, there we go, look at that, our table is empty and it got garbage collected. Now this stuff is pretty fantastic and all, but you're probably wondering, what is the real use case for weak tables? And I'm glad you asked. I'm going to show you some of the use cases that I'm actively using in a couple projects of mine. For example, in Paths of Peril, I am caching raycast parameters for AI objects in my game, because each AI has its own set of raycast parameters, and I'm putting it inside of a cache that has weak keys. Now, a table that has weak keys is also known as an ephemeron table, so pretty neat name. But because we are holding references to our AI objects with weak references in the keys, that means once this AI object is destroyed, or aka the AI in my game dies and its AI object gets destroyed, that also means that any of its raycast parameters that were inside of this cache also gets destroyed, and I don't have to clean it up manually. The garbage collector will do it for me, which is awesome. So to demonstrate this, I'm just going to put a temporary while loop in here. So while true do, and we're just going to keep printing out our include target cache every single second, and then we're going to hop into the game. We're going to play test. I'm going to kill some AI and have them get cleaned up, and once that happens and the AI get cleaned up, we should start seeing values disappear from this cache because garbage collection is getting rid of it for us. So if you take a look right now, I have a bunch of AI enemies roaming around my map. And because I have a bunch of active AI enemies, if we take a look inside of our cache, we can see all of their different raycast parameters. Now, if I were to kill all of these enemies, and I'm just going to do this by doing the kill all command. How did that guy even spawn up here? Once I kill all of them and I go back to my table, eventually it should start getting memory collected because there's going to be memory pressure from other things in the game. Let's focus on one of these. Like if I were to take a look at this first table, 17DA, whatever. Let's go to the most recent print and let's see if that table is still in there. Okay, that table is still in there, so it hasn't been garbage collected yet because I guess there isn't enough memory pressure. But I'm going to wait a few seconds here and see if it gets cleaned up. Okay, I've waited quite a bit longer. If we take a look at one of these tables, hopefully, we take a look at the first entry. Okay, perfect. It got cleaned up and deleted. So it handled it for me, got rid of it because that reference to that table was the only weak reference, got garbage collected, and I didn't have to do anything at all, which is awesome. Another example of me using an ephemeron table is right here inside of Salty Gun Labs. So I have this table of connections that's acting as a cache for specific button objects made by my GUI button class, which is a generic class of mine to add extra features and functionality and fun stuff to buttons. But once the button object is destroyed, I need it to be removed from this cache so I don't end up with a memory leak potentially in the future if tons and tons of buttons end up inside of this cache and I forget to clear them, which is why I'm holding references to all of these buttons with weak references. So that way, when this button gets destroyed, it's no longer going to be in the cache because garbage collection will clean it up for me. Now, another question you may have is, can I use weak tables to hold weak references to instances? And the answer is, it's complicated. And here's why. If we take a look at the Roblox documentation for meta tables and we head over to the meta method section and we look for the mode meta method, which is right here, you're going to see that there's a note here and that it's used in weak tables, declaring whether the keys and or values of a table are weak. Note, references to Roblox instances are never weak. Tables that hold such references will never be garbage collected. So I'm reading this and I'm thinking, really? So if I put an instance as a key or a value in a weak table, it doesn't consider that to be a weak reference and it's just going to keep it inside of the table. So I decided to test it. So back in Studio, let's go ahead and replace our key to be an instance rather than a table. We're going to create a new instance, and then we're also going to parent this instance into the game, into the workspace. So that way the parent is not nil and it doesn't get destroyed or anything like that. And then afterward, we will set the key variable to a different value. I mean, we could also do another part here, or we could set it to nil, whatever. But the main important thing is that we're no longer holding a reference to this part within our script, and the only reference to the part is going to be this weak reference. But according to the documentation, there's no such thing as weak references to instances, so this key and the value of hello should stay inside of our weak table forever. So let's test it out. If we go ahead and hit run and we take a look, what the heck? Look at that. The table is empty. Our instance was inside of the weak table, but then it got garbage collected. And you might be thinking, wait, why is it garbage collected? Isn't it still inside of the game hierarchy? And you're right, it is. Look, our part's right there. It's still in the game. And then I stumbled across this Devforum post from 2018. Weak tables don't work with instances. Might be a feature request, but weak tables don't work with Roblox instances. And they kind of give a same or a similar example to what we've done, and that the weak table will get cleaned up and it'll output nil. And they said, ideally, it shouldn't be garbage collected if they aren't parented to nil/destroyed XD. And then Stravant, an OG Roblox developer, gave this reply. You've unintentionally leaked an implementation detail of the engine. The way that the engine keeps track of references to instances so that it can give you back the same reference every time is by storing them in a weak table. Thus, if the only reference you have to a reference is itself in a weak table, then all of the references to it are in weak tables and it will get collected. There's no easy way to fix that either. The registry needs to be weak in order for the C++ side to know when the Lua side no longer has any references to an object not in the object hierarchy in order to destroy it. What you're effectively asking for is that an extra reference be held onto the object for as long as it's parented to the object hierarchy. But you can do that already by listening for the parent property changing. And he gives us an example here where this table acts as a way to hold on to the reference of the part even when it's within a weak table. But once the parent property of the part changes and we realize that it was parented to nil, essentially meaning this part is being destroyed, we get rid of the reference, make sure to disconnect this connection, and then it will work inside of the weak table. It says this will work as intended now. So actually, let's go test that out inside of Studio. So let's make another table in here. I'm just going to call it hold reference. And what we can do for this new part right here is that inside of our hold reference table, we can just, you just make a key and have the part be the key and then just set it equal to true. And then what we could do is we can listen for when this part's parent property changes. So we could do get property change signal parent. We'll connect a function to this event. And then we're also going to need to store the connection as well to disconnect it. So we need to make a variable outside here. We're going to call it connection. and then we're going to set connection equal to the RBX script connection that gets returned from this connect function. And we can check to see if key.parent is equal to nil, or you could say if not key.parent, then we need to get rid of our reference. So we can do hold reference key equal nil, and then we need to make sure we disconnect this connection. So as long as this part is parented inside of the game hierarchy, this should work and it shouldn't be garbage collected. So let's test it out. So if we take a look, what you'll notice is that, hey, it's no longer being garbage collected. But if we were to set the parent of this part equal to nil, it's going to be garbage collected. So let's actually do that through the command line. We could do workspace dot part. Oops, not parent, dot part. Dot parent equal nil. We hit that. Attempt to index nil with parent. Looks like we got an error. So we got that error because key gets set to nil down here. So actually when we go in the future, when this event gets fired, when we go to index key is actually nil. So parent does not exist within key because we set it to nil. So a way to fix that is we can instead call this our part. And then what I'm going to do is I'm going to make actually a do block. So I'll do something like this, do, and we'll do something like this, and we'll hold on to the connection. We'll put the part inside of the weak table, and then when you exit out of the scope of this do block, this part reference is not going to be accessible out here, and it should be garbage collected, but it's actually not going to be garbage collected because we're holding on to a reference here, and part's also being referred to within this function's connection, so it's an up value to this function. It shouldn't get garbage collected, but it should get garbage collected when it gets parented to nil. So let's find out. We run. It's in the weak table. We parent to nil. And there you go. The table is empty. It gets garbage collected and our part is no longer there. So this is why I'm saying it's a bit complicated, because the documentation states that weak tables can't hold weak references to instances as keys or tables, but obviously we know that's not true because the weak table is getting garbage collected. And something else I want to show you that further complicates this whole situation is if we have another script that has a reference to our part. So let's say we have another script in the game here, and let's make a variable that's going to refer to our part. So we're going to do workspace, and then we're going to have to do wait for child part because it's not in the game yet. This is a dynamic instance created during runtime, so we need to wait for it. But now if we hold a reference here, it's not going to be garbage collected here. And let me show you. So if we run it, and then we set the parent equal to nil, what you're going to notice is, oh no, it got garbage collected. What? I thought that this other script was holding a reference, right? Well, no, because this script isn't doing anything. It creates a variable, but then the script's over, nothing else in here runs, and this variable here, since it exits out of the script or exits out of the scope, it's not considered a strong reference to our part, so that part can still get garbage collected out of our weak table. So what we actually need to do is we need to do something like listen to an event inside of this part, like the destroying event, and connect a function to this event, and now we're going to be holding a better reference to part. But if we run the game still, and we set the parent equal to nil, you're going to see that, nope, it still gets garbage collected. Why? Why? Well, that's because we aren't referring to part. So if we do something in here like print part, aha, you see now, part is inside of this function. We're referring to part within this function that is active and alive because it's listening to the destroying event. So now, if we run the game, and we set the parent equal to nil, you're going to see that it will never, ever leave our weak table. You see? It's in there permanently. And you might think, well, that's pretty interesting. How the heck can another script holding a reference to our part prevent another different script from having its weak table garbage collected? And that's because this is all running within the same virtual machine. If you were in parallel Lulu and you had scripts underneath different actors executing in different virtual machines and they were holding references to parts, one reference to a part in one virtual machine won't be valid or known to the other virtual machine. That's why it can get pretty complicated pretty fast. Another developer has noted, stating that an easier way to do it is to listen on the entire game tree. And they give us this example code. Note, you can put this anywhere as long as an object has at least one reference somewhere, so across multiple different scripts even, it won't be collected. And of course, Stravant said, game.descendant added, always seemed pretty frightening to me performance implications wise. Have you actually used it in a real place? And the developer says, according to the profiler, more time is spent on other things. And then another developer said, if you add a lot of parts in succession, it becomes twice as slow or more, maybe. And they have a performance test here. And of course, the other developer states, adding 50,000 parts at once will be slow no matter what. In most situations, the difference seems pretty negligible. And Stravant says, on second thought, maybe it's okay. There's not really that many operations that result in a whole bunch of instances being added to the hierarchy at once. Most of the really large number of instance operations are moving big models between replicated storage class workspace, which wouldn't trigger it. I would still be worried about using it for mobile players though, since that extra script execution is a lot less free there. If you do something like copy a 100 instance GUI into your character, that's 100 extra times that the engine has to create a new thread and call over into Lua on it if you have that event hooked up. And he's like, for event listeners, Roblox reuses threads when it can. That's good to know. You see, this is such a wholesome Devforum post. Everybody's learning and talking about funny little things in the engine. But I do find it interesting that if we go back to the other page, it says, references to Roblox instances are never weak. Tables that hold such references will never be garbage collected. Maybe I'm not understanding what this means, but we can obviously see that that is not the case with our code here. Now, if we use that example here of holding references to objects when they are added into the game or removed from the game, we clean up the references and we go ahead and get rid of this other wacky implementation over here. So we could do part is equal to that, weak table, part, we could do part equal nil, something like that. We could get rid of this stuff right here, get rid of this table. We should be able to have the exact same behavior where this won't be garbage collected until that part has its parent set to nil. And we need to also ensure that this script is the one that runs first before this script, because we don't know which one of these scripts are actually going to run first. Because, for example, what if this script runs first and it creates the part and adds it to the workspace, and then this script runs? Well, guess what? It didn't have the opportunity to listen to the descendant added event and store that part inside of the hold references table. So a way that I'm just going to avoid that happening is we could do something really stupid like task.wait up here or something. We'll just do something like that. And we'll run the game and we'll take a look at our weak table, and you can see it's holding on to that part. So that's working. And then if we parent it to nil, it should get garbage collected. No, it doesn't get garbage collected. Ooh, wait, never mind. I take that back. It took it a minute, but look at that. It got garbage collected. So never mind. His system works. Pretty cool. So I've probably been babbling too much this video, and this video is probably already too long, but weak tables are cool, and they're interesting, and I think the documentation's wrong. But go ahead and mess around with weak tables. They're fun to see what you can do with them. Mess around with weak keys, weak values, weak keys and values, see what you can come up with. And ultimately, weak tables can potentially serve as a pretty good memory management tool. Otherwise, thank you for watching. I'll see you next time.